Good morning all. In this lecture video, we are going to discuss uh, analysis of recursive algorithms. In the previous video, we have discussed about how to analyze the efficiency of non-recursive algorithms. Today's lecture, we are going to discuss how to analyze the efficiency of recursive algorithms. Before getting into that example, we will discuss the general plan for analyzing the efficiency. The first one is you have to decide on the input parameter, which is going to indicate the input size. Then next you have to identify the basic operation of that algorithm. Then you have to check whether the number of times the basic operation is executed may vary on different inputs of the same size. In that case, we have to go for analyzing the efficiency of worst, best and average case efficiency. Then you have to set up a recurrence relation with an appropriate initial condition, which indicates how many times the basic operation is performed. The next, finally, you have to solve the recurrence by using any one of the recurrence solving method. So preferably we are using the backward substitution method. So before discussing the example, we will discuss what is a recurrence. So a recurrence equation is in the form of T of n. Okay, so usually which will be expressed or m of n in the form m of n minus 1 or T of n minus 1. Sometimes we'll call it as a recurrence or recurrence relation or recurrence equation. So it can be interchangeably used. Okay. So you have to find the closed form, that is T of n in terms of n alone. Okay, that is not T. So the first example, what we are going to discuss is factorial of a number. So this problem is very well familiar to you people. That is, you know that by definition, the n factorial is equal to n into n minus 1 factorial. N into n minus 1 factorial for all n greater than or equal to 1, and obviously the 0 factorial is equal to 1. Then we are going to write the recursive routine for finding what is the factorial of a number. You know that recursive function is a function which calls by itself. The more important thing what you have to consider while writing a recursive code is the first statement should be an termination statement. That is, otherwise the algorithm go into an infinite step. Always that you have to keep it in your mind. Whenever you are writing a recursive routine, the first statement must be an termination statement. So for here, the function is very simple. The name of the function is f of n, which is going to take one n positive number for calculating what is the factorial of n. If n is equal to 0, return 1. Okay, so that's why there's a 0 factorial is equal to 1. Otherwise, you have to keep on call this function recursively, that is f of n minus 1 into n by the definition of n factorial, that is n into n minus 1 factorial. So you keep on first, for example, if you are passing the value for 3, first it will pass 3, so n is not equal to 0, so which will calculate 3 minus 1, then it will go into this function, then 2, 1 and so on. Whenever if you have the value n is equal to 0, return. Finally all the values will be multiplied, then the value of n factorial is going to be returned. So in order to analyze the efficiency of an algorithm, according to the general plan, the input size is n. Okay, it doesn't vary for this same size of the input. So we'll find out what is the general efficiency. The basic operation is multiplication. Then the next step, you have to set up a recurrence, okay, which will indicate how many times the basic operation is performed. So the required recurrence is m of n, since the basic operation is m of n minus 1 plus 1, which means that you are performing this multiplication n minus 1 times. Then what is that plus 1 indicates that to multiply the value of n. Okay, that is f of n minus 1 into n. No, so that 1 is for multiplying f of n minus 1 into the value of n. While solving the recurrence, the initial condition is very important. That is m of 0 equal to 0, which means that when you are passing the value 0, okay, you are not performing any multiplication at all. You are not performing any multiplication at all. So it is if n is equal to 0, you are return 1. It doesn't perform any multiplication. Since that recurrence indicates that how many times you are performing the multiplication. So when n is equal to 0, you are not performing any multiplication. So that's why the initial condition m of 0 equal to 0. Suppose if the value n is greater than 0, okay, then we are performing m of n minus 1 plus 1 time multiplications. So by using the backward substitution, we are able to solve this recurrence. So this is what the required recurrence. So by using the backward substitution, you have to substitute what is the value for m of n minus 1. So in order to get what is the value of m of n minus 1, in this equation you can substitute n is equal to n minus 1. So m of n minus 1 is equal to m of n minus 1 plus 1. So m of n minus 2 plus 1. So in this m of n minus 1, you substitute the value of m of n minus 2 plus 1. So m of n minus 2 plus 1, as it is in this equation you are having 1, that 1. So if you simplify this, you will get m of n minus 2 plus 2. Then you have to substitute what is the value for m of n minus 2. So m of n minus 2 equal to m of n minus 3 plus 1. Again, to get that value in this equation, you substitute n is equal to n minus 2. So you will get m of n minus 3 plus 3. So in general, if you substitute m of n minus 3 or m for m of n minus 4 and so on, in general you will get it m of n minus I plus I. So you know that the initial condition m of 0 equal to 0, because we have to find out the closed form of that recurrence. So you have to bring this term to 0. M of n minus I, that term you have to bring into m of 0. So for that, if you substitute I is equal to, n in this, so you'll get m of n minus n plus n. So n minus 1 is 0. You know that m of 0 is 0. So 0 plus n, n. So therefore, if you solve the recurrence by using the backward substitution, you will get this m of n is equal to n. So therefore, the time complexity of that factorial of a number is equal to t of n is equal to big O of n. This is what the time complexity for finding what is the factorial of a given integer number n. So the next example what we are going to discuss is the Tower of Hanai puzzle. This puzzle is also very much familiar to you. Given 3 tower or 3 peg and given n discs arranged on one tower, you are supposed to transfer all the discs from tower 1 to tower 3. Otherwise, you can say this is the source tower, this is your destination. Okay, or this is your source, this is the destination, whatever we can have. So our aim is you have to move all the disks from source to destination. You can use one more tower as an intermediate one. There are some constraints for this towers of Hanai problem. The first constraint is at least the number of disks should be greater than or equal to 1. Okay, that is one disk, it's must. Then the second constraint is you can able to move only one disk at a time from one tower to another tower. The third constraint is you cannot place a larger size disk over the smaller one. That's why in this figure itself you can see that the disks are arranged according to the size. So you cannot place this larger size disk over the smaller one. Okay, so this is indicates that if you have to move only the 3 towers like that. Okay, the simple steps is first you have to move the n minus 1 disk from source to intermediate. Okay, then you can directly move the nth disk from source to destination. Then again you have to move this remaining n minus 1 disk from intermediate to destination using this as an intermediate one. So this is what the required algorithm in the pseudocode. Again, we are writing it as a recursive routine, towers of Hanai. So this is a number of disks. So this is a source. Okay. Then this is destination. This is the intermediate one. Okay. We can have as such. So this is your source tower name. This is your destination C. This is your intermediate. Okay. If n is equal to 1, you have to move disk from A to C. That is, you are directly moving the nth disk from the source disk to destination. Okay, otherwise what you have to do, first you have to move the top n minus 1 disk from A to B using C. So that is source to intermediate, using that destination as an intermediate one. Okay, so n minus 1 comma A comma B comma C. Now the look at this, the order is has been changed. Okay, so this keep on, this function will be called, okay, recursively whenever if n is equal to 1, again you are moving from A to C. Okay, so first you have moved from n minus 1 disk from A to B, then you are moving that nth disk from A to C, then the call will come here. Again you have to move that n minus 1 disk from that B to C using A as an intermediate one. So this algorithm is very simple. So when you come into this efficiency of an algorithm, how to analyze this is, first we have to find what is the basic operation. Here the basic operation is move, not multiplication. So that's why we named this function name as m. M of n is equal to 2 into m of n minus 1 plus 1. So which is very clear. First you are moving this n minus 1 disk from A to B, isn't it? So n minus 1 moves is required. Again you are moving the nth disk directly from source to destination, plus again you are moving this n minus 1 disk. So that's why the required recurrence is 2 into m of n minus 1. Okay, here n minus 1 moves, one more n minus 1 moves, plus 1. Then the initial condition is m of 1 is equal to 1, which means that if you have only one disk, how many moves is required? Only one move. So the initial condition m of 1 is equal to 1. Again, by using the backward substitution method, we are supposed to solve this recurrence. So 2 into m of n minus 1 plus 1. Again, you substitute what is the value for m of n minus 1. Get what is the value for m of n minus 1. Here you substitute n is equal to n minus 1. So 2 m of n minus 2 plus 1. So that's what m of n minus 1 is equal to 2 into m of n minus 2 plus 1. So for m of n minus 1 alone, you substitute the value 2 into m of n minus 2 plus 1. So you take the 2 outside. For m of n minus 1, you substitute 2 into m of n minus 2 plus 1. Here the 1 as such. Okay. So you simplify this. You take the 2 inside the bracket. 2 square m of n minus 2 plus 2 into 1, 2 plus 1. Okay. Again you substitute what is the value for m of n minus 2. So m of n minus 2 is equal to 2 into m of n minus 3 plus 1. For m of n minus 2 alone, you substitute this value. Again you take 2 square outside. So 2 into m of n minus 3 plus 1 plus this 2 as such. Again this 1 as such. Again you take 2 square inside this bracket. 2 cube m of n minus 3 plus 2 square plus 2 plus 1. Again, if substitute the value for m of n minus 3 as 2 into m of n minus 4 plus 1. So you'll get it as 2 power 4 m of n minus 4 plus 2 power 3 plus 2 power 2 plus 2 plus 1. Okay, so in general, we have to find out what is the closed form of that recurrence. So 2 power I m of n minus I. So here it is for 3, no? So 2 power I minus 1 plus 2 power I minus 2 plus and so on. Okay. So 2 power I m of n minus I plus, so there is an summation 2 power I which ranges from 0 to n like that. That is 2 power n plus 1 minus 1. That is the formula. Okay, so instead of n you substitute I minus 1. So you will get it as 1 1 which get cancelled, 2 power I minus 1. So that is a standard formula for this summation of 2 power. Okay. But what is the initial condition says m of 1 is equal to 1. So in order to achieve this, we have to substitute for I is equal to n minus 1 in this equation. I equal to n minus 1. So it will become 1. Okay. So 2 power n minus 1. M of n minus 1 plus 2 power n minus 1 minus 1. So this will become 1 no. So because m of 1 is equal to 1. So here you will get 2 power n minus 1 plus 2 power n minus 1 minus 1. If you simplify this, you will get it as 2 power n minus 1 minus 1. So obviously we get this time efficiency in the form of exponentiation. So you can write 2 into 2 power n by 2. Because here 2 power n minus 1 plus 2, if powers are equal, you can multiply in the addition. So 2 into 2 power n minus 1, 2 power n minus 1, you write 2 power n divided by 1, the 2 will get cancelled. So that's why it will coming as 2 power n minus 1. So the time efficiency of this Tabasov-Hanai problem is 2 power n, because we are going to consider only the order of the growth. The order of the growth is exponentiation. The third example is counting the number of bits in the binary representation of a decimal integer. Okay. Since we are going to again write this recursive algorithm, so the problem is very simple. For example, you have to find out how many bits in the decimal representation, sorry, in the binary representation of 4. Simply you divide this number by 2. So 2, the remainder is 0. Again you divide this number by 2. 1, 0. So our problem is you have to count the number of binary digits in the decimal representation of this 4. So 1, 0, 0. So the answer what we are supposed to return is 3, because the number of bits is 3. This is the statement of the problem. So the what we are going to do, this the logic behind in this is simply you divide this number by 2 until the n is greater than 1 or equal to 1. Okay, so that's why this, if n is equal to 1, you are going to return 1. Okay, else return, you are calling this function recursively. Simply you divide this number by 2 plus 1. So the plus 1, which means that whenever you are dividing the number by 2, you are incrementing the count by 1. Since we need the number of bits only, not the binary representation of that number. We are requiring only the number of bits in its binary representation. So whenever you divide the number by 2, you simply increment the count by 1. So we have to set up the recurrence. Okay, so the basic operation performed here is addition. Okay, so even though you are performing division, the basic operation what it is contribute most to the running time is, our aim is to count the number of bits, so that the basic operation is addition. Okay, so the a of n by 2, okay, and plus one more addition is made by the algorithm to increase the returned value by 1. So basically this kind of problem, we can say it is an information theoretic kind of problems. Since this problem input size, it depends only on the number of bits in this number. Okay, so actually you are every time you are dividing this value by 2. Okay, so this leads to the recurrence a of n is equal to a of n by 2 plus 1. Okay, again the initial conditions a of 1 is equal to 0. So which means that when the value n becomes 1, okay, we are not performing any operation. Okay, so that's why a of 1 is equal to 0. That's what the initial condition. If n is equal to 0, here you are not performing any basic operation at all. So how to solve this by using the backward substitution is, we have to use some standard approach. We have to solve the n in terms of 2 power k. Okay, n is equal to 2 power k. In that equation, you substitute n is equal to 2 power k. So a of 2 power k is equal to a of 2 power k minus 1 plus 1. Because a of n by 2, no. So if n is equal to 2 power k, then it will becomes 2 power k minus 1 plus 1. Again, the initial condition also you have to write in terms of 2 power 0. A of 1 is equal to 0. How you can write 1 in terms of 2 power? 2 power 0 is equal to 1. So by using the same substitution method, okay, you substitute the value for a of 2 power k minus 1 as a of 2 power k minus 2 plus 1. Again, in this equation, you substitute k equal to k minus 1. So a of 2 power k minus 2 plus 1. Again, in this one as such. So a of 2 power k minus 2 plus 2. Again, you substitute what is the value for a of 2 power k minus 2 as a of 2 power k minus 3 plus 3. So a of 2 power k minus 3 plus 1. This 2 as such. So you will get a of 2 power k minus 3 plus 1 plus 3. So in general, you will get as a of 2 power k minus I plus I. We know that the initial condition a of 2 power 0 is equal to 0. So you have to make this term is equal to a of 2 power 0. Okay. So what you have to substitute? Substitute I is equal to simply k. If you put I is equal to k, a of 2 power k minus k plus k. Okay. So we'll end up with a of 2 power k is equal to k, because a of 1 is equal to 0. So we know that what we have substituted for n is equal to 2 power k, and hence if you take logarithmic on both the sides, you will get k is equal to log n to the base 2. So therefore this efficiency of this algorithm is log n plus 2, log n to the base 2. Thank you.